apologies. So a wave is a net movement of energy without the net movement of a medium. Now we need to go ahead, and I've created another word. We need to go ahead and define what's a medium. So in one context, the medium is the average. In this case, the example that I'm giving you, the medium is the air. In Vian's, so now we're getting away from the math example, going into the physics example. What was the medium in Vian's example? Well, what is doing the saying of the goodbye? The hand. The medium is the hand. So a medium, and there's other definitions for medium. A medium is also what we call a fortune teller, if you want to go that route too. But in physics, when we're talking about waves specifically, if we're talking about the movement of energy without the net movement of a medium in this case is anything a wave travels through. So the sound's a really good example. You can hear me really clearly, but I don't see hair moving on any of you. It's not like my voice is causing wind in the class. Obviously, if you were sitting right in front of me, even here, like my hand, I don't feel my breath unless I really emphasize certain words. Like I'm not moving a lot of air, and yet you can hear me really clearly, I hope. If you can't, then I mean, you have a problem. I don't have the problem because I'm really loud. I know it. I can hear Mr. DeVries' class can probably hear me right now. So a medium is anything a wave travels through. So in Vian's example, the medium is the hand. And if it has without the net movement, it means that whatever the medium is, whatever the sound is, or whatever the wave is traveling through, it might move for a moment, but if it has no net movement, then the movement is immediately undone. So like in the case with sound, the sound is a wave. It's leaving my vocal cords, it's leaving my mouth, it's hitting your ears, but all it's doing is it's making the air vibrate a little bit, and then the air is going to hit the next air molecule. The one molecule bounces back, the next molecule bounces forward, but then that one's going to hit another molecule that bounces back, and so all you have is this jiggling back and forth of air molecules, and at the end of the day, when all the sound is quiet, the air molecules have returned back to where they started before I said it. Or in Vian's example, we wave, the hand stops, the hand has not gone anywhere, and we're done waving, and there is no net movement. We move, the hand is obviously moving. We good? Okay. The hand is obviously moving, but at the end of the day, the hand hasn't gone anywhere. So a wave is movement of energy without net movement of a medium, and a medium is anything wave travels through. Some waves require mediums, others don't. Sound is an example of a wave that requires a medium. If there's no air, if all of a sudden we were able to suck the air out of the room, I would go from talking like this to... which is really weird to think about. And we don't have one. We used to have one at school, and then it broke. If you put something in a vacuum chamber and then start to suck the air out, you will actually hear the sound disappear. It's really quite cool, but we broke our vacuum pump, and they're really expensive, so we don't have a new one. So it's a demo I used to do, which is a bit of a bummer. So some waves require mediums. Sound requires something to travel through. Sound travels pretty good through air. Sound travels really well through water. If you have, there's a kind of a happy medium where, no pun intended, where you have, it's thick enough so that the sound can really propagate. Sound travels really, really far in water. But if you're too dense, like a solid, like a wall, sound doesn't travel very well through walls, obviously. Mr. Keeley's class can't hear me, for example, but DeVries' class can. So a wave that requires a medium, we call a mechanical wave. So any wave that requires a medium is called a mechanical wave. So there we go. Mechanical waves require a medium. They have to have something to travel through. Examples of this are things like sound. What other examples of, yes, the waving high and the waving by? But what other things do we talk about that are waves that require mediums to go through? What are you familiar with already? Water. In the name, it tells you what the medium is. There is energy there. It comes from a host of different sources. But if you took away the water, all of a sudden that's not going anywhere. There's another rather unfortunate phenomenon that requires a medium to travel through. There was one yesterday in Tibet. Did anyone pay attention? Do you read the news for fun? What happened yesterday in Tibet? Happens often in that part of the world. And in our part of the world. Nobody? Anyone else take a guess? It was not a storm. An earthquake. Plate tectonics used to be part of the Science 10 curriculum, and it was great because you study earthquakes, and you would learn in Science 10 in the Earth Science section of that of that course that earthquakes, when an earth quakes, there's a couple different ways that happens. One is when one tectonic plate, which is the things that make up the surface of Earth, for those of you who have never taken it because Science 10 no longer teaches it, is when one plate slides under the other. They get stuck, energy gets built up, and when they release, one plate will slide under another, and a shock wave gets produced as a result. There are two different kinds of, and then there's ones where it slides horizontally. So we're living on one of these, where it's sucking under the other. The Pacific plate, actually it's the Juan de Fuca plate, is going under the North American plate. And so you get this, that's why we have so many earthquakes. And the entire Pacific Ocean, the Pacific Rim, those of you who don't know, is called the Ring of Fire for a reason. This whole zone, we've got one plate, and you can actually see it if you look at the map of the world, the one that I've got on the back of the class there. There is that lighter region in the middle. Actually, you know what? I'm just going to grab my laser pointer. Demonstrate this. Okay, take a look at the map on the back. This section, where it's lighter, means the ocean is shallower. So that section right there, and it runs all the way from, it cuts right through, it's really hard to stay steady, right through Iceland, all the way down through and up and around the bottom of Africa there. That's called the Mid-Atlantic Ridge. At the Mid-Atlantic Ridge, you've got a whole bunch of, that's where new tectonic activity is creating new crust. It's coming up out of the ocean, and North America, South America, Europe, and Africa are actually separating. They're traveling apart. Unfortunately, what that means is for these guys to travel apart, this piece here needs to go that way, and the Pacific plate is actually fairly large. This is not a great map for it, but it's this portion here. It's like east side of Africa. The Philippines are right there. Japan's right there, and it loops back around into Alaska, Western Canada, and these guys all the way down here. That's what's called the Pacific Rim. It's also called the Ring of Fire, and that's because all of the plates that are surrounding it, because this is where new plates are getting created, these plates are getting pushed left, these plates are getting pushed right, and this plate, that is the Pacific Ocean, is getting pushed underneath both of those other sections of plates that are getting pushed sideways. And so you get these earthquakes and, well, volcanoes, but earthquakes are not what I want to talk about. You get these earthquakes in very specific regions because of that. The Himalayas are another example of plates that are getting pushed up into each other. So actually, you know what? I'm going to grab a pen again for those of you who don't know where the Himalayas are, which is where Tibet is. I believe it's this region right here. North India, South China. You've got Nepal in there, you've got Tibet in there, and you've got plates that are, the Indian plate is pushing north, the Chinese plate, well, I don't actually know what that plate's called, is pushing south, and you get, instead of one going under the other, they're both pushing up. So you get this Himalaya, there's a reason why that mountain range is there, and it's because these two plates are pushing each other up. When they slip, when any of these plates slip in any way, you get these massive earthquakes, and earthquakes generate two different kinds of waves. They generate a wave called a P wave, and you get another wave called an S wave. Do I have it in here? I want to make sure I don't screw this up. And different kinds of waves require different kinds of mediums. Yeah, okay. So P waves, they do require a medium. P waves can travel through liquids and solids. But S waves can only travel through solids. And fun fact, this is how we know that the fact that these two waves propagate through different kinds of mediums actually tells us a whole lot about our Earth. When an earthquake happens on the other side of our planet, we can detect one kind of wave, the P wave, but we can't detect the S wave through the Earth. And what that means is if P waves only can go through liquids and solids, and S waves can only go through solids, if the P waves are the only, so if an earthquake happens in China, for example, and we go to detect it with our detectors in North America, and we only detect the S waves, we don't detect the P waves, but the European detections can detect the P waves and the S waves. It means there must be something liquid in the center of our planet. That's how we know, for those of you who have studied the Earth and the different layers, when we say, oh yes, there's a liquid layer in the middle there, elementary school students are like, oh yes, liquid layer, okay, cool. Very rarely do they have to actually stop it. How the heck do we know that? No one's ever drilled down there to see it. But the study of waves and knowing what kind of waves propagate through what kinds of materials actually tells us what's going on in places in our Earth we can't get to, which is really cool. I think it's really quite cool. So we know that because these waves propagate through different kinds of mediums, there's different materials in our planet, and we actually can take a look at, I mean, if a P wave is going through liquids but not through solids, what's your earthquake going to generate with a P wave? Depending on where it's located, a tsunami. And that's the energy provided by the P wave. So you've got all of these different kinds of mechanical waves. We've got sound, we've got water waves, we've got earthquakes. These are the most common examples that we give all the time. And so this chart here, it's a speed of sound in air and a relative humidity. So because sound requires air, anything that can change the air actually changes how sound propagates through the air. So the two biggest impacts are going to be temperature and relative humidity. Pressure does it as well. If your air is, if there's less pressure, there's less air, it's not going to travel as far as fast. So like at higher altitudes, for example, where the pressure is lower. But you can see here, like the speed of sound is roughly 330 meters per second or 335 meters per second. But depending on the temperature and the relative humidity, it changes. So if you're really cold and it's not humid, it travels at 331 meters per second. But if it's really hot and you've got high humidity, sound actually travels at 350 meters per second, or 351.2. So there is a 20 meter per second difference between cold with low humidity and hot with high humidity, which means if someone's yelling at you, you're actually going to hear it quicker if it's hotter and humid than you would if it was cold, which is, I mean, 320 meters per second versus 350 meters per second isn't going to be super noticeable when they're standing right next to you. Even down a football field, it's not a huge difference. It's not going to be super noticeable. But it's interesting that, I think it's interesting that this is an effect. So mechanical waves require a medium. Then there's a whole class of waves that don't. Electromagnetic waves do not require a medium. And the first electromagnetic wave that you are all aware of as human beings is visible light. Visible light is, well, again, the earliest experience of visible light for lots of us is the sun. The sun, it comes up in the morning, while the Earth spins, and now all of a sudden you can see the sun. It gets bright outside. There is nothing between the sun and the Earth, and yet the light makes it here. Light is a wave. There's a vacuum. Scientists used to think there was something there that allowed this to propagate. They used to call it the ether. Didn't know what it was. They gave it a name. They say waves need to propagate. Light is a wave. There must be something there. We know now that's not true. There's nothing there. Electromagnetic waves propagate themselves, and the fact that they are their own medium is weird and hugely foundational to parts of physics. The fact that light is both a particle and a wave. But in general, electromagnetic waves do not require a medium. This is the idea of wave-particle duality is the language there. The particle we call a photon. We've never seen a photon, except we only see photons. Like an individual photon we've never seen, but the only reason I see you is because I see photons bouncing off you. The light from the classroom bounces off of you. I see it. My optic nerve turns that into data that I interpret as you, whoever you are. Lena, Gernavin, Syra, Irde. If I can't see light getting to you, or coming from you, rather, I can't see you. So if I go like this, I slide over here, or if I just do this, all of a sudden, now the light from Gernavin, Hirde, and Syra is blocked, so they're not there. Except they are. Okay? So you get this idea of wave-particle duality. Electromagnetic waves are their own medium, and it's more than just visible light. Light waves look like this. They oscillate, they go up and down, and they cover a whole bunch of different spectra. That whole poster there that I started talking about yesterday is this section. You have, for waves that are big, you have large wavelengths, which we're going to talk about in a moment. You have, those are called radio waves. And as you decrease that wavelength, you get different kind. We use these waves differently. Radio waves are constantly going through us. Anywhere on the planet that you can turn on an FM radio and get a signal, or an AM radio and get a signal, that means there's radio waves going through you constantly. As you, and this, so the radio waves and even into the microwave band, that includes things like Wi-Fi. Anywhere you can get a Wi-Fi signal, electromagnetic waves are punching through you. They're low energy, so that's not a big deal. But as we start to up the ante here, that we get more and more energy. Microwaves we use to cook food by jiggling water molecules back and forth. The infrared, you are constantly emitting infrared. Infrared is what we call heat. Heat, going over the test yesterday, Diego, you missed that. Heat is the transmission of thermal energy. You guys are constantly emitting it because your body is constantly producing heat through its own cycle, keeping you alive. That heat has to go somewhere. And the outside world is colder than you, and so you radiate that heat out. You can see it. If you get night vision, or not night vision goggles, but infrared goggles, or even infrared camera, you can see, it's designed to see those waves leaving you. Yeah. Yes, but your body temperature, so your body maintains a temperature of roughly 36 degrees. 36. For some people it's higher, some people it's lower, but it's between 35 and 38 degrees. It is normal human healthy body temperature. When you are in an environment that is warmer than that, you will absorb energy from the outside, raising that temperature, which is why being outside on a hot day can be dangerous, because it's hotter than you're supposed to be. But anytime you go into an environment that's lower than that, now, if you remember back to last chapter, heat will always move from high thermal energy to low thermal energy. So if you walk into a room that's at a lower temperature, yes, it might be warm, but room temperature is in the low 20s. Like the definition of room temperature is in the low 20s, which is why we all have to wear clothes. Because if even in a low 20s room, that's lower than your body temperature, so you're going to be constantly emitting thermal energy. So the emission of thermal energy is going to make you feel cold. Anything that draws energy from you is going to feel cold. Anything that gives energy to you is going to feel hot. In Science 10, you would have looked at exothermic versus endothermic reactions. It's the same idea. So if you walk into a room that's at a lower temperature than you're at, if you're not wearing enough clothes, you're going to feel cold. You can get hypothermic in a room that is room temperature if you are naked in there long enough. It takes a long time because with the temperature that high, you're not going to get hypothermic very quickly, and it doesn't draw temperature from you, doesn't draw heat from you very quickly. But you can. Typically, we think of hypothermia being in like really, really cold water, but even like a lukewarm bathtub can get you hypothermic if you're there for long enough. It just needs to draw enough heat out of you faster than you're producing. Does that answer the question you asked? Okay. So infrared waves are heat, and then you get this really tiny sliver of visible light. This is the electromagnetic spectrum. The photons that we can see are in here, and depending on their wavelength, which again is a topic we'll talk about in a second, you get, different colors. This is where you get Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. And this corresponds to tinier and tinier wavelengths. Red has the largest wavelength, violet has the smallest wavelength. And as the wavelength gets even shorter, now you're into the ultraviolet, which we can't see, but there are animals that can. Bees, for example, can see the ultraviolet, and so the world will look different to them than it does to us. You have rods and cones. Your rods and cones are designed for visible light. Bees have another structure in their eye that helps them detect and see the world in ultraviolet, which is weird to even think about. And then as you crank up the energy, decreases the wavelength, now all of a sudden you get light that you can see through. X-rays. X-rays are designed to be, they're light, that's all they are, but they're light that's at a high enough energy that it can punch through your skin, but it's a low enough energy so that it bounces off your bones. So if you could see X-rays, you would just see everyone's skeleton. And then as you get higher and higher and higher, you get things like gamma rays, which is past the X-ray range. It's a photon, high energy, but it's so high that it can now start to damage your DNA. It's how you make the Incredible Hulk or various forms of cancer. And gamma rays are created at very high energy photon levels. So things like a nuclear blast, fission, stars exploding. You need massive amounts of energy to create gamma rays. Yes, here, Dave. Sorry? What do you mean? Oh, anything past gamma? I don't think so. Let's look at the poster. Gamma's as far as, so gamma's up here. You have really, really high energy, so like the frequency here is in the E hertz. What is E hertz? Here you've got P hertz, you've got T hertz, you've got giga, whatever. After giga, I don't know what that is. TP and E. I don't know what those prefixes are. So you've got the microwave band, you've got the infrared. There's two different kinds of infrared, far infrared and thermal infrared. This is the band that you're generating just by being warm. This is the visible light spectrum. Then you get into the ultraviolet. There's UVA, there's UVC is right there. Oh, there's UVA, UVB. UVA is right there, UVB is right there, UVC is right there. So these are the UV bands that we're concerned with why you wear sunscreen when you go outside. And then you get extreme ultraviolet, soft X-rays, hard X-rays, and gamma rays. And there is nothing past. No, you just crank up the, you can crank up the energy. I mean, there is a maximum that we've experienced, but like, I mean, there's nothing past gamma is, there's no reason, let's put it this way. There's no reason for us to define anything past gamma because gamma is where we start dying. Like if a gamma ray burst, and these things do exist out in the universe. If a gamma ray burst brushed over the surface of our Earth, it would wipe out all life. We would just cease to exist. That much energy in a photon, and enough of them, would effectively irradiate our planet so that it can no longer support life. What about what? Anything behind? Oh, radio. No. There's different classifications for radio. Like there's super low energy radio. Radio is the bottom, gamma is the top. Anything below, like radio is where it's so low frequency, there's nothing that we can detect or do anything meaningful with. And gamma is what ends life. So between what we can't do anything with or can't detect, and on the other end with what kills us, that's how we define the ends. And then everything in the middle gets split up depending on its usage. Good questions. Flip the page. Here we go. Lots of things to draw. This page is empty. Empty pages in my notes should make you a little bit afraid. Okay, so there are 3 types of waves. There's also, we've looked at 2 types, mechanical and electromagnetic, but there are more different ways to classify waves. And we're going to classify them based on how they move. 3 types of waves based on how they move. The first kind of wave that we're going to label is called a transverse wave. Now, transverse waves can be mechanical. Transverse waves can be electromagnetic. These things can travel through vacuums. Vacuum has 1 C and 2 M's. And solids. And so what this means is that if it can travel through a vacuum, it has to be electromagnetic, EM wave. Or if it can travel through a solid, that means it's some kinds of mechanical. Some mechanical waves are transverse waves. And a transverse wave is a transverse wave if the medium moves perpendicular to wave direction. So perpendicular means at a right angle. So if there's a, yeah. Okay. Okay. So perpendicular is at right angle. So if a wave is traveling from me to the door, if the energy is going that way, for a transverse wave, it means the medium, whatever it is going up and down. So an example of that, I've got my gigantic slinky over here. And we're going to use this. Alina, can you help me out? Move some stuff around. How many should it get? No, not yet. Now, Alina, I'm trusting you. I need you to not let go of your end until I'm ready for it. It's going to collapse back. Can you take it from the class? Please don't let go. So I'm going to send a wave to Lena. And so the medium in this case is the spring. So I'm going to demonstrate a transverse wave. The spring is going to move perpendicular, but the wave is going to go to lane. It looks something like this. If I said a bunch of waves, no, you need to hold it still as much as you can. So the wave's going, I'm generating it, Lena's feeling it, which means the wave's going that way, and the medium's moving up and down. I think one again. The one doesn't work super well. It's in one pulse, bounces back. But you can see that the medium, the spring is moving up and down. Okay, you gonna go? So that was it. That's an example of a wave that we call a transverse wave. Let's draw it. It looks like this. I'm gonna use but that much of the page. Okay. And I'm going to draw this one a little bit higher. I'm going to draw a dotted line right through the middle. So this is what the spring was doing effectively. As I was sending wave pulses down, the wave was moving this way. That's wave direction. The spring was moving up and down. And so because the thing's like it's moving off of this, so this level here is where this, when I was not sending a wave. We call that equilibrium. And equilibrium is whatever the thing looks like without the wave traveling through it. This dotted line here would have represented the spring as I was holding it and Lena was holding it and nothing was happening to it. But as you start to send waves down it, now all of a sudden you get these different properties. You get the wave, parts of the wave were going higher than equilibrium, parts of the wave were below equilibrium, and as I was, like if you looked at, ignoring the two ends, just looking at the middle of the wave, the distance from equilibrium to the top and the distance from equilibrium to the bottom, if I was doing it properly, and I think I was, you should have noticed that those distances should have been the same. So we can define them the same way. Both of these things here, these two distances are the same. We call them the amplitude. The amplitude is how big it is. It's one way to talk about the energy. The more I was pumping my end of the spring, the bigger the amplitude was. Amplitude we denote with the capital letter A, and it is the distance from equilibrium to these 2 points. Now we give these 2 points names. The bottom we call the trough, T-R-O-U-G-H, and the top of the wave we call the crest or the peak. And we define one wave to be a portion of the wave from one notable point, which I'll give you an example of that, one notable point to the equivalent notable point. And what I mean by that is this. When you've got a wave like this, that's a crest. This is the next crest. They are the same notable point. So this guy right here is one wave. The same point to the same point is one wave. And we call that distance the wavelength. And for the wavelength, we use this little symbol here. It looks like kind of a curvy upside down Y. That is the Greek letter lambda. You could measure it from crest to crest. You could measure it from trough to trough. You might measure it from this portion of equilibrium through one crest, through one trough, and to this point right here. Or you could measure it from trough here to trough here. Again, notable point to equivalent notable point. And it doesn't matter where you measure it from, they should all be the same. So crest to crest, this point to this point, or trough to trough, the wavelength is going to be the same for the wave, all the way through it. So I'm going to write down some of these definitions here. The amplitude, where do I want to put this? Yeah, I'll put it over here. Amplitude A is defined to be the max, I'll say deviation. So what I mean by deviation is either the upness or the downness from equilibrium. So max would be either equilibrium to crest or equilibrium to trough. The max deviation from the equilibrium. Whatever that value is. And wavelength, lambda, is the length of one wave. And it's, I'll put it over here, measured from one spot to the next identical spot. So that's a transverse wave. Anything that moves like this is considered to be a transverse wave. So transverse waves can travel through vacuums or solids, which then, by definition, sound is not one of these waves. So then what is sound? Sound is the next kind of wave. Number two, I will use a different color. Which color do I want to use? Orange. Wave number two. Slide down here. Wave number two, this is the second kind of movement a wave can have, is what's called a longitudinal wave. Longitudinal wave. These kinds of waves can travel through solids, liquids, gases, not through vacuums, only through solids, liquids, and gases. So the classic example of a longitudinal... Which one, longitudinal? Yeah. The classic example of this would be sound. And if a transverse wave, the medium travels perpendicular. In a longitudinal wave, the medium travels parallel. To wave direction. So let me demonstrate this again. Once you're done writing that down, Lena, use your hand again. Okay. So I'll go back to my definition of wave. Going back to my definition of waves. Waves is the movement of energy without the net movement of the medium. So this was our transverse wave. And as you can see, the spring isn't actually traveling to Lena. This was my transverse wave. The energy's moving, but the spring's just going up and down. can't see what I'm about to do move so that you can. I have to go on the ground for this one. Yeah, you could kneel on the ground as well. Make my life a lot easier. So transverse waves move perpendicular, longitudinal waves move parallel to. So if the wave is going to travel to Lena, the spring needs to be moving towards Lena as well. So an example of this would be a pulse that looks like this. You can see the waves jiggling back and forth, but it's not actually moving perpendicular to the wave. Go back, launch it straight down there, and you can see the pulse traveling down the wave. And that's all, so you're like, oh. And that's all sound is. Sound is air jiggling back and forth in the direction that my face is pointing. So this one's a lot harder to draw. So this is how I'll get you guys to draw it. Looks like this. So we will call this equilibrium. And then what we're going to do to demonstrate that there's a pulse of wave, perhaps you saw it when the slinky was moving down. As the pulse moved towards Lena, you saw, I'm hoping you saw, that packet of energy was denoted by a tightly compressed section of the spring moving down. Well, the spring itself wasn't moving, but that wave was propagating as a compression in the wave, or in the spring rather. So we're just going to draw it. Looks like this. I'm going to put a bunch of lines closer together. And then we'll do them far apart again. So how many do I have there? 4. 1, 2, 3, 4. And then I'm going to put 5 close together. 2, 3, 4, 5. And then 4 further apart. 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4. And so you get sections of this that you can tell, especially from a distance, maybe drawing it right in front of you. It's going to be harder to see, but especially from a distance, you should be able to see that we have big chunks where the medium is more compressed, and you get chunks with where the medium is further apart. So we have the same kinds of definitions. We're going to have an amplitude, or we're going to have wavelengths, but in this case, the amplitude is this. The amplitude A, right there, and we're just going to define it right here, is the closeness of compression and the amplitude of a sound wave, for example, directly correlates to its volume. So the louder you're experiencing something, the tighter this compression must be in whatever medium you're experiencing the sound traveling at you in, whether it's water or air. The tighter the compression, the louder the sound. So this is loudness in sound, for example. And now if we're going to look at wavelength, it's the same. It's the length of one wave measured from one spot to the next identical spot. So typically how we measure wavelength is we go from the center of one compression to the center of the next compression. You don't have to. You could go from beginning to beginning or end to end. But the center of compression to the center of compression is an easy way to do it. This is wavelength. The definition is the same, so I'm not going to redefine it there. It's still lambda. And it's still defined as being the measure from one spot to the next identical spot. So center to center is a great way to do it, but yeah, you don't have to do it that way. And then the last definition that we're going to have on this one, on the transverse wave, everything was moving perpendicular. There was the upness and the downness. On the longitudinal, you get a section where there's a lot closer together, and then spread wider. This widest spread here we call rarefaction. And for a longitudinal wave, the rarefaction is the area of widest spread. So you get the transverse wave and you get these longitudinal waves. Now, there really is no other way to move. Either you're moving perpendicular or you're moving parallel. The only other way you could move is if you combined perpendicular with parallel, and now you're moving in kind of a rolling pattern. Because if you combine forwards and backwards with up and down, now all of a sudden you're just rolling. When you're ready, flip the page. There should be some more blank space there. And we're going to get our third type up at the top here. We're going to get what we call surface waves. Did I do it the same way? Yep. There we go. Surface waves. And you can think of surface waves two ways. Either a surface wave is neither longitudinal nor is it transverse, or you can think of a surface wave as being a combination of transverse and longitudinal wave. It's both. And these kinds of waves occur, and the reason we call them surface waves is because these occur at the edge of a medium. So the best example of a surface wave would be so at the edge of a medium where two different mediums interact with each other is your water waves. You have water as one medium, the air is another medium. Water is a lot denser, waves travel a lot clearer through them than they do the air. And so you get a wave that looks like this. And if you're actually able to study these things, like if you could look at a wave tank, what you would see here is that the particles in the wave are actually just doing this. They're just rolling around in a circle. And the water isn't actually circulating, unless there's a current. The water's not actually moving forward. The energy is moving forward, and the water that's present is just rolling in a big circle. You get the longitudinalness and you get the transverseness. It creates a circle. Now, we're actually able to combine, physicists have, studying these things, have discovered that there is a connection, a correlation, between some of these different properties. Here it is. This is the universal wave equation. The universal wave equation looks like this. V is equal to lambda over T V is what you would expect it to be. V is wave speed. Lambda equals wavelength. And T equals period, or the time it takes one wave to occur. So the speed of the wave is equal to its wavelength divided by the period. But we also have another way to talk about dividing by a period. Dividing by a period is the same thing as multiplying by the frequency. Because F equals 1 over big T, another way that we can write this thing is that the speed of the wave is equal to the wavelength times the frequency. And this guy here is the best example of the wave equation. So the speed of the wave is equal to your lambda times your frequency. And, lots of ands, I keep building towards something, because light and all electromagnetics, the entire electromagnetic spectrum, all of these things move at the same speed. Everything on that chart, the poster underneath Darth Vader, whether you're a radio wave, a microwave, visible light, infrared, ultraviolet, X-rays, or gamma, regardless of where you are, you're moving at the speed of light, which is c. So for light, the wave equation looks like this. C, the speed of light, is constant in the universe, which is beautiful, equals lambda f. That means there is a direct correlation between the wavelength of the light and its frequency, because this value right here, c, is constant, which is really cool. This value right here is constant. It's basically 3 times 10 to the 8. It's actually a little bit lower. It's 2.99 something times 10 to the 8. But for what we're going to be doing, we call it 3 times 10 to the 8. Oh, I'm totally going to get it done. I love it. So I'll do one example, and then I'm going to leave you some stuff to play with. A sound wave, whatever it is, has a frequency of 192 hertz. And it travels the length of a football field in 91.4 meters in 0.271 seconds. What's the speed of the wave? What's the wavelength? What's the period? And if the frequency changes to 442, what is the new wavelength and period? So sound travels at the same rate. As long as the temperature doesn't change, as long as the humidity doesn't change, a sound wave will move at the same rate. It doesn't matter if it's loud or quiet. It doesn't matter what the pitch is. It's going to move at the speed of sound. So let's take a look at this. What is the speed of the wave? Well, we know the sound's not going to be accelerating. Once it gets generated at the source, it's going to hit you, and it's not going to accelerate along the way. We know the distance that it covers. We know how quickly it does that. So v is going to be equal to the distance traveled divided by the time it took. So it's going to be the 91.4 meters divided by the 0.271 seconds. And for the sake of time, I'm going to give you these values. If you do that calculation, and that's in seconds, you're going to find that the speed of sound here is 337.27 meters per second. I'm going to flip back. You don't have to. Because interestingly enough, that could tell us the temperature and the pressure. No, the temperature and relative humidity. 337. You're looking at something like 10 degrees with 10% humidity. We could go outside right now, and this is what would happen, basically. That's fun. So there's our speed. What's the wavelength? Well, we know... Sorry. We know the speed v is 337.27 meters per second. We just calculated it. We're told what the frequency is. We know that the frequency of this sound is 192 hertz. To give that some meaning while you're writing this down. That's this sound. This is what you'd hear on the football field, traveling 91.4 meters in 0.271 seconds. And we want to find lambda. I'm just going to let this play. Apparently it'll play for an hour if I let it. I wouldn't. That's really annoying. So we want to find lambda. We want to find the wavelength. We've got the wave equation. We know the relationship between the frequency, the wavelength, and the velocity is this. So v equals lambda f. So 337.27 is going to be equal to the lambda times the frequency, 192. Divide both sides by 192, and I'll give you the value for the sake of time. The wavelength is 1.76 meters, which means the wavelength for this sound is that. This sound makes a wave that goes forwards and backwards this big. You don't see it, but it's got real physical meaning. The question says, what's the period of this wave? We'll take that away. The period of this wave, period, is equal to 1 over the frequency. So period is the length of time for one blast of that wave. So that's going to be 1 over 192. That's going to be 0.0052 seconds. And for the sake of time, I'm going to give you that value. What happens if we change that frequency? Now it's no longer 192, now it's 442. 442 hertz. Boom. So now it sounds like this. That is A on the piano, for those of you who are musically inclined. We went from that lower to this now higher pitch. How is that going to change things? Well, that frequency is higher. So what's the new wavelength in the new period? Well, wavelength is equal to the velocity over the frequency. I'm just rejigging the wave equation. The speed of sound does not change. So this is going to be 337.27 divided by 442. This new wavelength is 0.76. So a higher pitched sound has a shorter wavelength. And the period is just going to equal 1 over the frequency. So 1 over 442. And you're going to have, I'll give you the value here, is 0.0023. Still very quick, about half as big as this one. Shorter time to experience the wave once. And so now you start combining these notes, you start combining these waves, and now you're generating music, which is really cool. So that's it. I'm done for today. We'll start talking about some of these properties of waves later. I know I haven't given you a ton of time. Here's what I would like you to look at. There are 12 questions there, and I'm going to assign half of them. I want you to do 1, 3, and 5 from the first chunk, and I want you to do 2, 4, and 6 from the second chunk. It connects the stuff that we did yesterday, period and frequency, with the wave equation that I've given you today. And there it is. Oh, there's one question I didn't assign that's actually really good. Oh, dang. Question 2 and 6 there are actually relate to the stuff that we've talked about today. So if you had finished those first 6 and wanted to look at 2 and 6 on the first chunk, that wouldn't be a bad idea. This one's about sound coming from your voice and echo in the air. And this one is exactly what I was doing with the spring. So don't pack up yet, because there is still time left in class, guys. Come on. There's 4 minutes. Has it been raining early all day? I've been paying attention. Okay. This is what I want you to practice. You can practice it at your leisure. If you're tired and done hearing me talk, you can pack up. Man, 2 weeks off, you think you guys come back with some more energy? 2 weeks off, you're more tired than when you left. Yeah, because you destroyed yourself for 2 weeks. The number of grade 9s that have like, yeah, I was up till 4 AM playing video games every day. It's like, and now you come back to school and you're an absolute mess. I can appreciate that. So there you go.